Okay, so today I want to talk about section 4.1 and 4.2 from the textbook. Mostly 4.2. And that has to do with higher order linear homogeneous differential equations with constant coefficients. So we've just spent a good amount of time talking about second order linear homogeneous differential equations with constant coefficients. And then we went on to talk about second order linear non-homogeneous equations with constant coefficients. But recall, given a second order linear homogeneous equation, differential equation with constant coefficients. So in other words, something like ay double prime plus by prime plus cy equals 0, we know that there is the general solution is parameterized by two parameters. Usually I refer to those parameters as A and B, and of course if I give you a initial value problem, if I give you initial conditions in addition to the differential equation, you can solve for those parameters. And of course the actual form of the solution has different forms depending on the form that we end up with when we solve the characteristic polynomial. So the general solution depends on the solution to the characteristic polynomial. So the characteristic polynomial associated to this differential equation is going to be ar squared plus br plus c equals 0. And if we solve that, so if we have two distinct real r's, r equals, let's call them r1 and r2, where r1 and r2 are both real numbers, we know the solution to the original differential equation has the form a times e to the r1t plus b e to the r2t. If we have a repeated root, then y of t has the form, so let's call our repeated root r just equals r1, but it's repeated twice, so we have r minus r1, then our solution has the form a e to the r1t plus b times t e to the r1t. And of course, if we have complex roots, we have two complex roots. So let's say r equals alpha plus or minus beta times I when we solve the characteristic polynomial, two complex roots, because they have this I there. Then we know the form of the general solution y of t equals a e to the alpha t cos beta t plus capital B e to the alpha t sine beta t. And you can put the cos and the sine in any order you want. Obviously, the order doesn't matter. So this is what happens when we solve a general second order linear homogeneous differential equation with constant coefficients. Now I want to talk about higher order equations. So higher order equation have degree 3 or more. And we know that an nth degree polynomial has n roots up to, so an nth degree polynomial has n real or complex roots. If you account for multiplicity. So if we account for multiplicity, so a root could appear multiple times, in which case it would count as many times as it occurs, then we have n real or complex roots, just like a second degree polynomial has 2 real roots. So even in case 2, where it seems like we have only 1 real root, that root is repeated twice, so it counts twice. So let's talk about the solution to these higher order differential equations. So the general solution to an nth degree linear homogeneous differential equation with constant coefficients will have n parameters. A second degree has 2 parameters. A first degree generally has 1 parameter. This is going to have n parameters. Instead of referring to them as capital A, capital B, capital C, and so on, where I could easily run out of letters, I'm just going to call them capital A sub 1, capital A sub 2, all the way up to capital A sub n. Those will be my parameters. So for every distinct root R1, I'm going to have something of the form a number times e to the R1t. If this is for a real root, of course. For a repeated real root, So for a real root R1 repeated, let's say k times, I will have terms of the form a1 e to the r1t plus a2 times t e to the r1t plus all the way up to ak t to the k minus 1 e to the r1t. So if I have a repeated root, if it's repeated twice, I'll just have the first two terms here. If it's repeated 3 times, I'll go up to a3t squared e to the r1t, and so on. And for complex roots, so for distinct complex roots, let's say r equals alpha plus or minus beta I. Again, I will have terms like I had over there. A times e to the alpha t times cos beta t plus, I'm going to call it A1, plus A2 e to the alpha t sine beta t. And I suppose I might as well tell you what happens if we end up with repeated complex roots. So for complex roots repeated k times, we end up with this. A1 e to the alpha t cos beta t plus A2 e to the alpha t sine beta t plus all the way up to, let's see, 1, 2, so I guess that's a to the 2k minus 1 t to the k minus 1 cos, I forgot my e to the alpha t cos beta t plus a2k t to the k minus 1 e to the alpha t sine beta t. So this is for repeated complex roots. So this is actually easier than it might look at first blush. And in the next video, I'll run through an example with you.